Thank you, Minju. Well, thank you for having me. This is my title slide. It's a long and wordy title, and it has two very strange pictures on it that I'm going to explain a couple of slides from now. So Minju gave you a little bit of my biography. I was asked to tell you just a little bit more about myself before I started the talk, so I have one slide on that. So this was me at school. You can see from this, importantly, I'm originally from the UK, and I was a beautiful, angelic child. After school, I went off to school in Scotland. So this is me on board the school boat in Scotland. I did my A-levels there, and that's the first time I met one of your teachers, Miss Thomas. So I tried very hard for all of you, you should know this, to find an embarrassing photograph of her from, let's just say, many years ago. Couldn't find it, so I could only find one from a couple of years ago, which is not so embarrassing. Then I went off to Cambridge, where I did my undergraduate degree in mathematics. And I stayed around and I did a master's degree in mathematics and theoretical physics. And from there, I sort of made a big change in my life. I moved to the United States, and I went to Brown University, which is an Ivy League university in the northeast of the US, for those of you that don't know it. And I did my PhD there entirely in theoretical physics. And then after that, the life of an academic is very sort of itinerant for a while. I bounced around doing postdocs. I was at MIT and various other places. And about 10 years ago, I was recruited to the University of Pennsylvania to direct the newly formed Center for Particle Cosmology there. And I've been there, as I said, for about 10 years now. And I look a lot older there here than I did in this beautiful angelic photograph. So what I want to tell you about today is a flavor of the kind of work I do. And I'm going to try to do it without any equations, obviously, which makes it a challenge. So some of you have been in the classes that I've been in today, and some of you will get bored with the explanations I give here, but for some of you it'll be new. So back to these pictures on the first slide. A long time ago, when I was a beginning professor, at the beginning of my career, I went to give a set of lectures at the Honors College in the University of Oklahoma. And it turns out, for reasons that I was really surprised by, the University of Oklahoma has an amazing history of science collection. One thing they have is a sort of original edition of Tycho Brahe's astronomical letters, 1596. And I got to touch this, which was amazing. And these are his personal emblems from the front and back of the astronomical letters. And this one here has an inscription on it, and that inscription says, Despiciendo suspicio, which means, by looking down, I see what is above. And you can see here, this figure is looking upwards, and yet here he's got all the sort of tools of alchemy underneath him. And this one says, Despiciendo despicio, which means by looking up, I see what is below. And again, this person's looking up at the sky, but, and learning from it about the Earth that is sitting here. And so if you take nothing else away from my talk, it's that the kind of work I do is supposed to be the modern day version of what is embodied by these front and back pieces of Brahe's astronomical letters. And that is that for Brahe, he was saying you can use alchemy and astronomy to illuminate one another. And what I'll be saying is that nowadays we're in exactly the same position, except we don't really have alchemy, we have particle physics, the physics of the tiny. And so my talk is really going to be about that. So I'm going to be talking a lot about the universe. It's probably good that we tell you what the universe is, at least what's in the universe. So here's a picture of our galaxy as seen from Earth. This is a beautiful dark sky. Here is the Milky Way. You see that because we live in a galaxy that is a plane, and so all the stars sit mostly in a plane, and when you look in the plane, you see them all shining back at you, and when you look away from the plane, you don't see so many of them. So you really see here the fact that we live in a galaxy. And I think you'd agree that this is very, very beautiful. Galaxies look like this from the outside. Big flat plane, incredibly beautiful, big bulge in the middle, very, very hot, lots of stars, billions of stars all glowing. And again, very beautiful. And for people like me, we just don't care. We don't care that they're beautiful, we don't care that they're made up of stars, we don't care that they're mesmerizing. All I really care about is that they're dust for me. So how many of you in class have done this thing where you take iron filings and you put a magnet under a piece of paper and you spread iron filings in? The iron filings show you what's going on with the magnetic field. And you don't care that they're iron filings, you don't care at all. You just care that they're there because they tell you about the magnetic field. And for me, people like me, galaxies, those beautiful, mysterious things, are just the iron filings of cosmology. They're out there in the universe, and by looking where they are and how they move, I can figure out what space and time are doing, what the universe itself is doing. So for us, they're sort of boring. So all I really care about galaxies is that they're gravitationally attracted to one another, and what that can teach us about the universe itself. So how do you do that? So the first thing you do is you use something called the Doppler Effect. So the Doppler Effect is something that you know very well for sound. And so here's an example of the Doppler Effect for sound. You're going to be standing by the side of a road, and a car is going to come past at a constant speed. Because it's at a constant speed, the car has an engine. That engine's emitting a noise. And if you were in the car, you'd just hear that noise. It would just be, that would be it. If you're standing by the side of the road, this is what you see and hear. So two things happen there. Firstly, of course, the sound gets louder when the car gets close to you, but that's not the bit I care about. The bit I really care about is, you hear how the note changed? You hear the note of the horn got higher and higher and higher, and then became deeper as the car passed you. And what's happening there is, sound is composed of waves. The waves are, beat, 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 beat. But as the car comes towards you, it emits one wave, and then the car moves towards you and emits its next beat, and then it moves towards you and emits the next beat. And so the note of the car engine as it moves towards you consists of sound waves that are closer together than they would have been if the car was stationary. And so you get a higher pitched note. Similarly, when it goes away from you, you get beat and the car moves away. And a longer distance between the sound waves, lower frequency note. And that's why you hear this weird effect. So this is the effect that you hear all the time when you're standing by a road. It turns out this is also true for light. Okay? So light, sound has pitch, high, low pitches. The equivalent of pitch for sound for light is the color of the light. So if you have an object which is emitting light in all directions, let's say white light, and then that object starts moving in a certain direction, the light waves in front of it get bunched up. And because of that, they change color, and they become more and more blue. And the light waves behind it get spread out and become more and more red. That's just exactly the same as this Doppler effect for sound, but it's for light. Okay? So why is this useful? Well, if I told you that I had a car and I let you listen to the sound of its horn, and then you close your eyes and all you could hear was the sound of the horn as the car was moving, you would be able to tell me, by comparing that sound to the original sound, whether the car was moving towards me or away from me, because it was either higher or lower. And we use that same effect for stars. And so stars emit light in a very specific way. In particular, their light is emitted in the spectrum, if you break it up into different colors, that has a very distinct pattern. We know that from our own star, the sun. So when we look at faraway galaxies, we can use this same principle to find out if galaxies are moving relative to us. And that's what cosmologists like me, well, not really like me, but the experimental version of me do. So here, the first time this was done effectively, it's about 100 years ago in the US. This is Edwin Hubble, probably the most famous American astronomer of the last century. Hubble is sitting on a very hard chair in a three-piece suit in front of the Hooker telescope on top of Mount Washington, California. And this is the way all cosmologists dress, even today. And he's looking at distant stars and galaxies. And if he sees one of them that has light like the light that our sun emits, but bunched up, that means that the galaxy is moving towards him. If he sees one that has light like our sun's light, but stretched out, then it means the galaxy is moving away from him. And in that way, Hubble was able to figure out whether faraway galaxies are moving at all. And you might think, well, maybe some are moving towards us and some are moving away from us. Who knows? And the answer turned out to be much more interesting than that. So here's what Hubble saw. By the way, here's Hubble again, three-piece suit, tweed suit, smoking a pipe. Again, this is what I'm like in my office, if you're wondering exactly like this. And he discovered an amazing fact. All distant galaxies, with no exception, as long as they're far enough away, are moving away from us. And furthermore, they're moving away at speeds that are proportional to their distances. So here's Hubble's actual data. This is how you know Hubble's a genius, because he drew a straight line through that data. So this is speed, kilometers per second. This is distance in weird astronomers' units, megaparsecs, but big distances. And this scatter is remarkably fit by this straight line. So if something is a distance of 1 megaparsec away, it's moving away at 500 kilometers per second. If it's 2, it's moving away twice as fast. This is what Hubble discovered. And if you worry that that is, that you would look at that data and draw a line like that through it, don't worry, so would I. But fortunately, you can take data like that Hubble had, and you can make it much more up to date because we have better telescopes these days. If you use better telescopes, the data looks like that. And that's sort of amazing. Notice, by the way, the distance has changed here. They're not 500 kilometers per second. They're 10,000 and 20,000, and they're much further away. So we have exquisite data on faraway galaxies these days, and the data falls along a beautiful line. So when people tell you that the universe is expanding, this is what it means. Faraway galaxies are moving away from us. Their speeds are beautifully correlated with how far away they are from us. Okay. So when you look at the night sky, it's really like looking at the pages of a book, because the sky itself that you look at is two-dimensional, right? You don't have any feeling when you look at the sky how far away things are. If you see a particular object in the sky, it could be a big object that's very close, that's far away, or a small object that's very close. How would you know the difference? Okay. And what Hubble allows you to do is figure out the order of these objects. It allows you to construct the dimension of time. Okay. So you look at the night sky, you see these objects. They all look like they're just painted on a sphere around you. But by figuring out how fast they're moving, you can extrapolate to how far away they are. And that allows you to know the third dimension. Does that make some sense? So it's a very powerful technique. And by using this, we can sort of reconstruct the history of the universe, because faraway objects, all these objects are sending light to us. Faraway objects are sending light to us that took longer to reach us, because light travels at a finite speed. And so when you're seeing light from these faraway galaxies, that's telling you about the universe when it was much younger than the light that's coming to you from these close by galaxies. So this is a tool to get at the history of the universe. Now, everything I just told you was just an observer looking through a telescope. How do you put that together with what's really going on in the universe? And for that, you need theoretical physics. And here's Einstein. Everyone always shows pictures of Einstein as a crazy old man with, white hair and just looks like someone's dragged him through a hedge backwards. So I always like this picture of Einstein looking rakish and sort of, interesting. So Einstein taught us that the theory of gravity is not what Newton had taught us. It's something completely different. So what Einstein taught us is gravity, the way in which things are attracted to one another or behave when they are near each other, things with mass and energy, is equivalent to the bending or warping, if you like, of space and time by matter. Okay? Now that's a very sort of highfalutin concept, and I'm not going to use any of that really in this talk. But what matters for this talk is just a very simple version of this, and that is the way in which the universe evolves, the way in which things decide to be moving away from us or towards us, the way in which that time is ordered in the universe depends on the stuff that's in the universe, and vice versa. So there's an interplay here between stuff in the universe and how the universe is growing. And when you take Einstein's theory of gravity, you learn something really surprising, and that at a time was just independent of what you had seen on the last slides, but when you see them together, it's quite striking. So you learn this. So here, by the way, is Einstein in a more traditional look, looking through that same telescope I showed you with Hubble, still smoking the same pipe in the background, watching Einstein look through this telescope. So this is sort of, I like this picture a lot because it tells you how lucky we were in the early part of the last century to have amazing observations about the universe at the same time that new theoretical developments were taking place. So here's what Einstein's theory tells you. It tells you if you have a couple of places in the universe, and I'll just label where they are by X and Y at a given time, then if you wait a while, this is just a theoretical prediction of his theory. And if you wait a while, the distance between those 2 points will increase. Okay? So that sort of fits nicely with what I told you on the last slide. So the fact that the universe is expanding seems to be explained by Einstein's theory of general relativity. And this, like I say, this all happened, in the late sort of 19-teens, early 1920s. So now we have a great theory and a great set of observations. Is that the end of the story? Obviously it's not. So what goes on after this? So one thing you might wonder is, what determines how quickly this happens? You know, this goes from this size to this size. How do you know how fast it happens? And the question is, here's where all the details are. The expansion rate of the universe, how quickly things grow apart, depends on what's in the universe. And it depends in detail on what's in the universe. So you're all made of regular matter. You're made of protons and neutrons and electrons. How much of all those is in the universe affects how quickly the universe expands. If there's things you've never thought of that are out there in the universe, their mass and their energy, everything about them changes how this expansion rate works. And so looking out at the universe and using this Doppler Effect trick of how quickly things are receding from us is a way of figuring out what's in the universe, what kind of stuff is out there. And that's a lot of what cosmology is. So here's what's going on. This is a two-dimensional picture of what the universe might be like. Imagine that you live on the surface of a sphere that's expanded. And all your galaxies are painted on the surface of a sphere, and all those galaxies are sending light to one another. And what happens is, as the sphere expands, the light from different galaxies heads towards us, and because the sphere is expanding, the light wavelength gets spread out, so it starts off, say, purple, and then goes blue and green, and eventually ends up, say, as red as it reaches us, because the universe is expanding. So that's what I meant by using the Doppler effect and light to figure out what's happening to the universe. So this is a remarkably successful theory, Einstein's theory of gravity, Hubble's observations of the expanding universe. And everyone should know that this is a fact about the world. It's been known for 100 years, and it's incredible. Okay? But every time you have an advance in science like that, it throws up completely new questions. And this was no exception. So what are the problems that you are faced with once you understand that the universe is expanding? And here's the problems. Well, here's some of the problems. If you go on into the universe, you take a sufficiently big chunk of the universe, much bigger than galaxies or clusters of galaxies, huge chunk, and you just figure out, using this technique or any number of other techniques, what's in that region of space. And by which I mean, what kind of stuff is out there in the universe. You learn something amazing. You learn that about 4% of the universe, that's all, is made of the stuff you're made of, is made of atoms. So of all the stuff that you measure out there, 4% is this. This is why chemistry is boring. This is 4% of the universe. Apologies to the chemists. Amazingly, 22% of the universe is something we have really no understanding of. We call it dark matter. I'm going to tell you more about it in a while. But we don't know what it is. And it's at least 4, maybe 5 times as much of the universe as all the stuff that makes up all of you and all of the Earth and everything you've been used to thinking of. Even weirder, about 74% of the entire energy and mass in the universe is a completely weird and odd type of stuff called dark energy. I'll tell you about this too towards the end of today, but what this is doing, it turns out, is causing the universe to accelerate. And when we get to that time, I'll explain what I mean by that. There's a whole host of other problems of modern cosmology that I won't even talk about in this talk, but if you ask me questions later, I can tell you a bit about. There are questions that I might call origins questions. Why is the universe so flat? Why is it almost homogeneous, meaning looks the same everywhere you look? Why did galaxies form at all? These are all questions that we have some answers to, but they're thrown out by applying Einstein's theory of gravity to this expanding universe problem. But for now, in order to sort of get you thinking about this connection between the large and the small, let's focus on one of these questions, and that is, what is the nature of dark matter? So first of all, I should convince you that dark matter is out there. After all, it's not that convincing if I just say, there's a big chunk of the universe, trust me, a lot of it is dark matter. So let's see if I can do better than that. So there are a lot of ways to understand that there's dark matter in the universe, but I like this one because it's very, very visual. So Einstein taught us that gravity is bending up of space because of energy and mass. And so one thing you realize quite quickly, if you understand that, is here's the night sky that we see. But the night sky that we see involves light coming to us from very, very far away, all the way through to our telescopes. And as that light comes to us, it has to go past all the stuff that's in the way. Galaxies and anything else that you can't see. And those galaxies and anything else that you can't see bend up space and time so that the path that light rays follow are not necessarily just a simple straight line to us. They can, in principle, bend because of the presence of all kinds of things in the way. This is something we call gravitational lensing, because it's a very similar effect to if I just put an optical lens in the way of light. If you've got light coming to you and I put an optical lens in the way, it bends the light, and you would know that there was a lens in the way. Similarly here, the light is bent by mass and other energy in the way, and it distorts what you see in the night sky. So how big is this effect? So here's an extreme version of it. Here's a picture that you all know. You've seen this picture many times. It's a picture of Einstein. And all I'm going to do is take this picture and put a microscopic black hole right in front of his nose. So small that you won't see it. And just to be clear, what I'm going to show you is not an artist's conception. What I'm going to show you is exactly what you would see if I put a big enough black hole right in front of his nose. The black hole would be so small you wouldn't see it, but it would be very gravitationally important. And the light from his picture coming to your eyes would get bent. So what would happen to that picture? It would look like this. Okay. So that's sort of dramatic. Let me show you again. So the light that is now coming in a straight line from his face to you now gets bent by a big massive object that's in the way that you can't actually see. But it has great effects on the light, and that's what it is. So there's two things to take away from this picture. One is that towards the center, all kinds of crazy things are going on. You're seeing multiple pictures of Einstein with even weirder hair, and he's upside down. That's all what you might call strong lensing. I'm not really interested in that here, but for the record, it's because light is coming from the picture and wrapping around the black hole many times and coming back out to you. That's amazing, but for another time. But far away from the black hole, from the big mass, you see how the eyes get stretched out into these arcs, and the chin gets stretched out into this arc, and the mustache gets stretched out into this arc? That's a thing that happens all the time whenever you have a big mass in the way. And so if I gave you a picture of Einstein that you knew, and then I showed you this picture, you could realize, you could figure out what was causing this distortion. And then you would infer, oh, there's a big black hole sitting right in front of his nose. Okay? So if I gave you the two pictures, you could figure that out. And this is exactly what we use when we think about the universe. So how does that happen? Well, here's a picture taken from Hubble Space Telescope, the Hubble Deep Field. Almost everything you can see on this picture is a galaxy. Itself composed of billions of stars. Okay? And right here is a cluster of galaxies, so many galaxies clustered together. And you see all these arcs that are on the sky? What those are galaxies. They're not galaxies that are spread out along the sky. What's happening is there are galaxies far behind this cluster of galaxies, and the light's coming around this big cluster and getting bent out, just like Einstein's features got bent out by that black hole. And so, if I give you a picture like this and you understand the sort of statistical properties of what the sky should be like, you can figure out what's in the way. And with Einstein and a single black hole, it's not that hard to do. With a picture like this, you need a supercomputer to do it, but you can do it. So here's what you do. You take a supercomputer and you ask, what's in the way? So let me orient you on this picture before I make it bigger. Here is the sky. You've got angle that way and angle that way. And on this picture, there's an angle that way and angle that way. And the vertical axis is how much stuff is in the way. Does that make sense? So it's a reconstruction of what's getting in the way of the light. So there are several things to take away from this picture. One is there are lots of spikes. Those spikes are where the actual galaxies are, those glowing things. Very dense, lots of mass, big density of stuff in the way. But the other thing to take away from this is you see this hump, this smooth hump that rises like this, goes away, much bigger than the size of an individual galaxy. That's, if you added up how much stuff is in that hump, it would be much bigger than all the spikes added up together. That's dark matter. That's something that you could not see in the previous picture. It wasn't glowing, you would have no idea it was there, but by looking at this effect, this lensing, you infer the existence of a truly huge amount of mass and energy that's in the way that you just couldn't see. And that's what we call dark matter. So it seems that that stuff is really particles. How do we know that? It's really some kind of matter. We just don't know what kind of matter. And the way we know it is through Well, there are lots of ways we know, but there's one particularly interesting way we know it, and that's this. So what you're seeing here is, on the left, a picture, again from the Hubble Space Telescope, of two galaxies, two clusters of galaxies, I should say. Here's one cluster of galaxies, a big cluster. And here's a little cluster of galaxies. Do you sort of see where I'm pointing? A big cluster of galaxies and a little cluster. This picture alone doesn't seem to be telling you very much, but I'm going to tell you in advance now that we know that this little cluster has punched through this big cluster of galaxies. And for that reason, this is called a bullet cluster. It's punched through. So how do we know that? We know it because Hubble is not the only telescope we have out in space. Here's a picture of the same system taken from what's called the Chandra X-ray telescope. The Chandra X-ray telescope, unless it isn't obvious, measures X-rays. And that's nice because most of the matter in those clusters of galaxies is just gas between the galaxies. And when they collide, when one punches through the other, that gas bangs into the other gas, slows down, and heats up. And this is a picture of the X-rays emitted by that. So just to be clear here, this sharp front you're seeing here is a shock front like you would see in a supersonic jet or a bullet that is many, many, many thousands of galaxies across. It's a shock wave. And because this bullet galaxy is punched through this one here. So this glowing gas shows you where most of the regular matter is. And the previous picture I showed you, this one, has all kinds of little arcs in it that show you where most of the mass is. So you could ask the question, is most of the mass where those clusters of galaxies are, the glowing stuff? Or is most of the gas where the glowing stuff is? Or is it where the clusters of galaxies are? And the answer is, when you put the two things together, you get this. Almost all of the regular matter is in this glowing red stuff. And almost all of the total matter is here. And so in a system like this, what's happened is the two galaxies have come together, two clusters of galaxies have come together. They've got red regular matter and blue dark matter. As they go through each other, the dark matter just goes straight through because it doesn't do anything. The regular matter slows down and heats up, and so they separate. And then you can use the satellites, one of them to see where the regular matter is, and one of them to see where the dark matter is. So systems like this tell us that not only is there this sort of abstract notion that there's something out there and we don't know what it is, it tells you that it's made of particles. We don't know what those particles are at all. But the one thing we do know about them is they don't shine like regular particles do. So the question for people like me is, what is this stuff? Okay? When I take some complicated picture of the universe like this and ask what is bending up space and time in that picture, then into such a complicated picture like this, the question is, what is it? What is that stuff? Okay? Now, everything I've told you about so far doesn't sound like it's got anything to do with the physics of the timing. This is all about astronomy and cosmology. But once you start asking questions like, what are the particles? That's a very different kind of question. So to understand what dark matter could be, you have to start thinking in a completely different way. So let's go to the other end of the distance scale. I was showing you just then clusters of galaxies banging into one another, the biggest things we know of in the sky. And I was telling you that they told us how the universe itself behaves. So the largest scale things you could be asking about. Now let's go to the other end of the distance scale. Here's an atom. It's 10 to the minus 8 centimeters across, tiny. And atoms themselves, we know, are composed of electrons that are essentially point-like. All we know is they're less than 10 to the minus 16 centimeters across. And nuclei that are not point-like, not 10 to the minus 12 centimeters across. These are tiny numbers, right? And the nucleus is composed of protons and neutrons, which are even smaller than the nucleus itself. And protons and neutrons are composed of quarks, these strange particles that are essentially point-like. And we learned all this over the last century, not by looking at the universe, but by doing the opposite, by going to laboratories and smashing particles together at ever higher and higher energies so that we split them apart into their constituent parts. And from doing that, we found out that, first of all, things are made of atoms. Secondly, those atoms are made of nuclei and electrons, etc., etc. But we discovered more than this. By doing these experiments, we discovered that all of these different parts of matter, these microscopic scales, are all governed by just 4 fundamental forces of nature. So everything you know about the microscopic world, and in fact, the universe up to this stage, are described just by 4 known laws of nature. And those laws are gravity, that I've already talked about. But then there's the electromagnetic force. You start studying this in school. It's the thing that describes how magnets behave. It describes how electrons, charges behave and repel each other, et cetera, et cetera. And then the nucleus itself is described by 2 different forces, one called the weak force, that's responsible for things like radioactive decay, and one called the strong force, which is the thing that holds protons and neutrons together. So it's very strong, and that's what makes nuclei exist at all. So I don't want to go on and on about these forces. What I want you to understand is that this is a very complex story, but remarkably, just these 4 forces explain everything on those previous slides, and the big difference in length scales. Why electrons are so small and point-like, and why clusters of galaxies are so big. So it's a big range of phenomena described by just 4 relatively simple forces. So you could ask the question, I told you the universe is getting bigger today. Faraway objects are moving away from us. If you buy that, and I showed you data to show you that it's true, then in the past things were closer together. And in the far past things were even closer together. If you keep running that clock backwards, you very quickly get to a situation where all of the matter you can see is heaped on top of all the other matter. When you do that, very strange things happen. In particular, you know that when you start pushing things together under pressure, they heat up. And so, if you believe that things are getting further apart today, one consequence of that is that at very early times, the universe was small and it was very hot. And so one thing you can ask is, what happens to particles, be they electrons or protons or the things I'm trying to understand, this weird stuff called dark matter, in the early universe? And the answer is this. So I can describe what happens to particles in this sort of simplified way. So you can think of this a little bit like the way you write down equations in chemistry, but this is really particle physics. So, I have a couple of particles, A and B. If I smash them together at high enough energy, then they make a couple other particles, C and D. And typically, if you can get A and B together, and this releases energy, then it'll just happen. So it's very similar to chemistry in that way. But in the early universe, temperatures were so high, and these densities were so high, that particles were banging together all the time at very high energies. And in particular, particles are what are called our antiparticles, things that if they meet just become pure energy, could easily get together and what we say annihilate into just lighter particles or pure energy. This happens in the early universe all the time. It doesn't happen today because particles are very far apart. It's very unlikely that they get together, and if they do get together, it would take a lot of energy, and where's that energy going to come from? But in the early universe, there's a huge amount of temperature. They're all crushed together by the universe being small. It happens all the time. And so what can happen is that heavy particles can bang together. Something happens. This is like the Far Side cartoon, a miracle happens. This is particle physics. And lighter particles, like the protons you're made of, come out. Okay? And that's time running out. So this leads to the following picture. This is a figure taken from a Scientific American cover article that I co-authored some years ago. You've got the beginning of the universe. When the universe was hot, let's say. It expands. Particles are banging into each other all the time, creating and destroying. I write dark matter here, but it's true of any matter. But sooner or later, while they're banging into one another, eventually they become so dilute that they can't meet anymore. And whatever amount of matter you have left over at that point is just stuck there in the universe because there's just not enough density or temperature to bring things together and have them interact with one another. So you go from an early hot phase in the universe, creation and destruction of particles, including the stuff that you're made of, but also any other hypothetical particles out there, to a later time when they just interact a few times, to a final time when they're done interacting, and whatever happened here determines how many of them are left over at the end, and it stops. This is a process that cosmologists call freeze-out. Now, the number of particles you have left over at the end here depends sensitively on a couple of things. It depends on how massive the particles are, depends on how the universe evolves, and depends on how strongly they interact. If they interact with the electromagnetic force, it's a very strong force, then they annihilate very effectively and there's not much left over. If they don't, then they stop interacting sooner and you have a lot more of them left over. So It really depends on the kind of particles you have. So, remarkably, the dark matter abundance, the fact that there's 4 to 5 times as much dark matter in the universe as the stuff you're made of, that happens through this process if you have particles that interact with each other just through the weak nuclear force, one of those 4 forces that I told you about. And it didn't have to be this way at all. So that is a very suggestive fact. And it makes you think that if you probe the weak nuclear force, you should be able to understand maybe where dark matter is coming from. And I should say something I said before. Here's a little graph of all the particles that we know exist, the things you've heard of, quarks, electrons, more exotic versions of electrons, the Higgs boson, et cetera, et cetera. None of these things can be the dark matter. We know that. Okay, so it has to be something new. And if it's something of the type I just told you, interacting weakly so that as the universe evolves, it naturally ends up with 4 to 5 times the amount of matter, of it compared to regular matter, then it's what we call a weakly interacting massive particle, a WIMP. So WIMPs are a candidate to be the dark matter of the universe. Okay? And what would this be? It would be a new particle, stable, because it has to live the whole history of the universe, and it has to be at the weak scale. And that means that it should be within the reach of the world's biggest machine. So this is a connection to the physics of the tiny that we learned about from looking at the universe through telescopes. So it might be that we can find this. It might be that we can make this dark matter for ourselves. So how do you do that? Well, here's a view that you of all people should know, not from here, of course, but you know, this is by my standards very close to where you are. This is CERN, straddling the French-Swiss border. It's a huge particle physics laboratory, and underground is this immense circular collider that smashes things together, and at different places along that collider are different experiments. And I've highlighted a few of them here, but the one I personally care about is what's called the Annales Experiment, because at Penn we built quite a bit of that detector. We doesn't mean me, I don't do anything like that, but I have smart colleagues who know how to do it. So this collider already did something amazing, which you presumably have heard of. Okay? Here's CERN in 2012, July 4th. This was the press conference. They discovered the Higgs boson. These are the people who were responsible for primarily building the Large Hadron Collider. This is the announcement that they discovered this particle that people have been looking for decades, the Higgs boson. By the way, that's the Penn press up there. Our graduate students hung it on the wall and they pressed it. And very soon after this, so these are the people, 5 of the 6 people who predicted this boson, this Higgs boson. One of them had passed away already. And not long afterwards, 2013, Nobel Prize for Peter Higgs and Francois Englert. So the Large Hadron Collider already has had an amazing impact on physics through this. But it turns out it can do more, as I was describing on the last slide. Because the hope is, I told you that in the early universe, you can have these weird particles, let's say dark matter. They annihilate into the matter that you're made of, but sooner or later they stop annihilating, and you have some left over, and maybe it's enough to be all that stuff we saw in the galaxies. Now, if that's true, it turns out we can do the opposite. So what I told you about is you take a couple of weird particles, let's call it dark matter, you smash them together in the early universe because you've got a lot of energy, they produce protons. Time running that way. But if you can do that, if you can put enough energy into particles, you should be able to do the opposite. Take regular matter, smash it together, and make exotic matter. In other words, just turn this into action on its head. So this is a hard thing to do because these particles are very heavy and these particles are quite light. So Einstein taught you that energy is mass times the speed of light squared, E equals mc squared. So you can exchange energy for mass, but you have to have a lot of energy to make the extra mass to turn these things into that. So the Large Hadron Collider is a place where you can do that. So here's how the Large Hadron Collider works. It has a sequence of accelerating rings that take a proton, one of those nuclei, and speed them up in increasingly bigger circles. And I'm showing you just 2 here, but they really come in bunches of millions. And then it sends some of them out one way around the ring, and some of them out the other way around the ring. It speeds them up to an appreciable fraction of the speed of light. And when they get fast enough, you tweak a magnet, and they come into alignment, and you smash them together right in the middle of an experiment. And they hit each other, they vanish into energy, and that energy itself fragments into a whole bunch of particles that you then measure by building sophisticated electronics and detectors all around the collider. The size of this thing here is about the size of this ceiling in total diameter. Okay, so the reaction happens about where you can see on the screen, and you measure it out here on the ceiling and the floor. And by carefully monitoring all the particles that come off, the hope is that because the Large Hadron Collider measures things exactly at the scale of the weak interactions, that you can in fact make dark matter. So that's the hope. You search through the debris of these collisions at the world's largest machine, and you make dark matter. And if we can do this, this is one of the next big targets for the Large Hadron Collider, to do this and discover what the dark matter is. There's this very tight connection between the physics of the tiny, smashing particles together into their constituents, and figuring out what you see on the largest scales on the sky. And those two things are intrinsically connected. Okay, let's return to today. So I told you about dark matter that we think is determined by the physics of the early universe, the way I described it. What about what's going on in the universe today? So let's turn to the most important thing in the universe. Okay? I told you about dark matter. That's 22% of the total energy in the universe. Let's go instead to this other 74%. Instead of calling it dark energy for now, I'll just say what is causing cosmic acceleration. I'll explain what I mean by that in a minute. So remember Hubble. I told you that Hubble went and measured faraway galaxies. He figured out by looking at them carefully how quickly they were moving away from us. And by doing that, he could construct how the universe had evolved over time. You keep looking at further away galaxies, you find out how quickly they're moving. You say, well, the universe used to be smaller, and the far past it was a lot smaller, etc., etc. Okay? So in the last 20 years or so, people have learned how to construct, how to use Hubble's technique in an amazingly more powerful way. So I've called it here Hubble on steroids. Okay? So the goal here is to do exactly what Hubble did, figure out very carefully how far away things are and how quickly they're moving, but to do it for things that are much, much, much further away than Hubble could ever do. And the goal of that is because then, the further away I look, the earlier in the universe I'm seeing. If I can look far enough back, I'll get a very good picture of how the universe evolved over not just a relatively short time, but quite a long time. That'll teach me something deeper, hopefully, about the universe. So the way you do this is quite remarkable in itself, so I'll just spend a moment giving you a simplified version of that. So if I had a bunch of 100-watt light bulbs, and you knew they were 100-watt light bulbs, and then I gave you each one of them, and you went out across the campus late at night in the dark, I could figure out in principle how far away you were from me. And the way I would do that would be, I would say, well, that's a 100-watt light bulb. How much of that light is reaching me here? I know that the light leaves the light bulb, spreads out in a sphere, and the further away I am, the less light hits me. And there's a very simple mathematical formula that tells you how much. And so if I can measure how much light is hitting me, and I know it's coming from a 100-watt light bulb, then I can figure out how far away the light bulb is. Does that make sense? So that would be great. If we had 100-watt light bulbs in the universe, or ideally things that are much more powerful than 100-watt light bulbs, we would be able to see them across the entire universe, and we could figure out how far away they were. Until recently, we didn't have anything like that. In the last 20 years, it turns out we do have something quite like that. Something whose brightness we know very well, and is incredibly bright. And that is a certain class of exploding stars. They're called Type 1a supernovae, and they're quite amazing. To show you how amazing they are, let me show you, over here in a moment, I'm going to show you a galaxy. Now remember, a galaxy has billions of stars in it. Every one of them shining with at least the power of our own sun. And you're going to see one of them explode, and the light that that gives off will be about the entire light of the whole galaxy for the time that it's exploding. So here you go, I'll show it again in a minute. See that? So remember, this entire light is billions of suns shining light at you, and yet you can see clearly one, just a single one, as it explodes. It's that bright. And we know, not just so it's very powerful, very bright, but even better, it's about the same brightness every time one of them explodes. And the reason is, this is a special class of star that comes from binary star systems, where one star is slowly eating the other star. And eventually, it gets so big that it can no longer sustain itself as a star, and it collapses and explodes. And because it does it slowly by eating the other star, It's not like I have a lot of big stars of different sizes and eventually they have different sizes of explosion. They just keep eating until it reaches the right size to explode. And so it's the same power every time. So it looks something like, I'm going to show you what it looks like in a second. I should say, because of that, this gives us a very accurate distance measure, very far away in the universe. So here's what it should look like. Just to be clear, oddest conception. So you've got one star here that's just eating the matter from another star, accreting it. And it just keeps doing it over many, many, millions of years, until finally it just has the right amount that it can't sustain itself, and it just goes immediately, like an explosion. And that explosion is so big that it's seen across the entire universe. Okay? So these things are very powerful, these type 1a supernovae. And so you can use them to construct the history of the universe. So here's the history of the universe on a plot. So let me explain this plot to you. It's kind of busy, but it's simple plot actually. Here is the size of the universe. Here is time. Time is measured in billions of years from today. So negative numbers are in the past. Like minus 10 billion years is 10 billion years ago. The size here is measured in the size of the universe today. So today is 0 years ago and 1. Okay? And all of this data here, where my dot is the data that Hubble collected a long time ago. And the lines that you're seeing on this plot are different versions of how the universe could evolve in time by taking Einstein's theory of general relativity and saying, let's put a little bit of this type of matter in, let's put a little bit of this other type of matter in, and playing around with it. And depending on how much matter you put in, of which type, the universe expands in different ways. But you notice that no matter what you did, as long as you make sure it's right today, this little bit of data here couldn't possibly distinguish between all these different possibilities. That little dot of data in here, they all look the same as far as it's concerned. So you know the universe is expanding, but you can't really tell which of these types of expansion is going on. Does that make sense? But those supernovae, those exploding stars, allow us to see back not just a little bit of time, but almost back to 10 billion years ago in the universe. And that's, the universe is 14.1 billion years old. So you're seeing back here to, far more than 2/3 of the age of the universe in these exploding stars. That allows you to very carefully figure out what the expansion of the universe looks like. And something quite remarkable was shown. So not only is the universe expanding, getting bigger over time, but it's doing so faster and faster and faster. So it's getting bigger over time, but it's getting bigger faster. It's accelerating. And that is a mind-blowingly odd thing about the universe. It's mind-blowingly odd because the universe is, it's an odd place governed by Einstein's theory of general relativity, but it contains stars and galaxies. And stars and galaxies are all big, massive objects. And one thing you learn about gravity is gravity's attractive, right? So all those things attract one another. So yeah, the universe is getting bigger, but surely it's slowing down because of all these attractions between the things in it. And indeed, that's what everyone thought was happening until about 20 years ago. 20 years ago, they discovered this. The opposite is happening. It's speeding up. Now, I told you that Einstein told us that the way in which gravity behaves, the way in which the universe expands, depends on the stuff that's in the universe. So Einstein has a set of rules. I tell you the stuff that's in the universe. Einstein's theory tells you how the universe behaves. Or if you like, you measure what's going on with the universe, and Einstein's theory tells you what stuff must be causing it to behave that way. So if you trust Einstein's theory of gravity, then this implies there must be something very odd in the universe that we don't see, that is not dark matter, and is not the regular matter you're made of. It's much more mysterious than either of them. And it has to be behaving in such a way that it causes the universe to accelerate. And we call that, for want of any other name, dark energy. It's a terrible name, but we call it that. People confuse it with dark matter all the time, which is unfortunate. It's very different. So what could this dark energy be? Again, everything I've said here is to do with cosmology. What does this have to do with the physics of the time? So this is almost certainly the biggest question in modern cosmology today. I've spent most of the last decade working mostly on this problem. So it was discovered in 98, I should say. So about 20 years ago it was discovered. And in 2011, the Nobel Prize was given for this discovery to these guys. So that's for discovering it. That's for discovering that the universe is accelerating, but not for telling us what's causing it. So that's the big leftover problem now, this biggest question in modern cosmology. So what does that do with tiny physics? Well, one question is it in the same class as dark matter? Namely, you've discovered something by watching the motion of objects, in this case accelerating. Do we infer from Einstein's theory that there's some new stuff out there? Is it dark energy? And if it is dark energy, what it turns out we could be measuring, and this is a strange thing to say, is the weight of empty space. That's a strange thing to say, so I should probably explain that before you, even Claire looks very puzzled by this. So you'd think empty space would be as advertised, right? Empty. So what do I mean by that? But it turns out you can never have empty space. If I take a pat, go out into the darkest regions of the universe and start removing anything that's there to end up with a little patch that has nothing in it, what'll happen is, I'll take all the protons out of it and all the dark matter out of it and everything else. There are no particles left. All I'm left with is what we call the vacuum. Okay, that is the definition of empty space. But the physics of the tiny, quantum mechanics, doesn't allow that to remain that way. All the time, particles are popping in and out of existence. And this is something you learn from, you might think this is an abstract statement, but all of your modern electronics rely on this notion to some degree. These particles are popping in and out of existence all the time. So for tiny amounts of time, a particle, say an electron and its antiparticle appear, and then they recombine into nothingness again. This is happening all the time. It's a very weird effect. Okay? These are what are called quantum fluctuations. So even empty space is bubbling with these kinds of things. So it's a very sort of bubbly, energetic place, even empty space. And so you might wonder, Einstein taught us space and time behave in a certain way when you've got stuff in it. So what about this stuff, the quantum bubbling of empty space? Does that have a weight? Does that affect the universe? And it turns out the answer to that question is both amazing and incredibly worrying. So the answer is, those quantum fluctuations that I call them have exactly the right properties to cause the universe to accelerate. And if they do, they would be an example of what Einstein called the cosmological constant. So this is amazing. If they have the right magnitude, their properties are perfect to cause the universe to accelerate. And the really worrying fact is if you compute the size of the effect, you find that you're wrong by 10 to the power of 60. So this is the worst prediction in all of science. Okay? So we know we shouldn't brag about this. Okay? So obviously this is wrong. And so on one sense, there's something you have to understand here, which is that the tiniest physics you can think of can have an enormous effect in the universe. But we also know that the effect it should have is so big that it can't possibly be the answer that we're looking for. So something has to cancel this off, stop this from happening. We don't know what that is, by the way, but it has to be there because this definitely doesn't happen. If the universe expanded this much, then you wouldn't even be able to see your nose in front of your face because the light from your nose, before it reached your eye, would just be gone. So we know that that's not true. Okay. So if it's not that, what could be causing this cosmic acceleration? And the last thing I'll mention here is this possibility. There was a story just like this that played out over a 50-year period, well over a century ago. People were looking at the motion of planets around the sun, and they noticed that when Mercury went around the sun, instead of going around the sun in a nice ellipse or a circle, like you think planets should do, according to Newton's theory of gravity, instead Mercury comes along, and this is a very exaggerated picture, I should say, but it tries to go in an ellipse, but then the ellipse moves. It goes around like that, but then the ellipse moves. And it goes like this. So the ellipse sort of so-called precesses around the sun as time goes on. In Newton's theory, that doesn't happen. This was very puzzling to people. And in fact, people postulated that this was due to some new dark component in the universe. They didn't really call it that. Leverrier came along and said, well, the reason this happens is there's a planet, there's another planet. It's on the other side of the sun, so we don't see it. It's dark to us. But its gravitational effect changes what Mercury does. And so you can predict the existence of a new planet this way. And they even gave it a name. He called it Vulcan. And we know now that this was not correct. We know now because Einstein came along. And in fact, his theory of gravity perfectly explained why Mercury did this. In fact, this is a little quote about general relativity about how it explained the motion of Mercury. And so this is an example of an effect where there was some unknown motion that was discovered by observing the motion, the motion of, in this case, planets in the solar system. You inferred the existence of some new object that was causing it because you thought you knew your law of gravity perfectly. And the answer was no. All there is the sun, but the law of gravity was wrong. And so you could ask that question here about the most mysterious question in all of cosmology. You could ask, is there a similar story? Is cosmic acceleration, the fact that the universe is getting bigger faster, a canary in the mine telling us that there isn't any new dark energy out there? You've just got regular matter and dark matter. But the laws that tell you how space and time behave due to that stuff are just not the ones that Einstein thought were right on the biggest scales of the universe. Maybe gravity is different. And that's something that I won't go into any detail about in the talk, but that we've spent a huge amount of time working on in the last decade or so. And it's just a fascinating area of research, and no one knows the answer to this yet. And my own opinion is that despite the fact that I'm getting paid to work on it, we won't solve it in a short time. And so it might be that one of you solves it eventually, or maybe your children will solve it. But it's a very, very deep question. So what have I tried to explain in this talk? I've tried to explain that there's 4% of the universe, that's all, that's made of the stuff you're made of. It's a really tiny amount. And although I didn't talk about it, it turns out we don't understand that very well at all either. Because it turns out that in the early universe, there should be a lot of the matter that you're made of, but there should be about an equal amount of the antimatter that you're not made of. They should just meet one another and go away. So how come there enough matter is left over to make stars and planets and you? That's a problem that we haven't quite solved yet, although we suspect the answer is relatively simple. 22% of the universe is dark matter. We don't know what it is, but we know that it governs the growth of galaxies and stars and planets, and hence you. And if you want to understand its secrets, 22% of the observable universe, then we may have to do it by breaking the atom into its tiniest constituents and sifting through the debris of that to find out. We've also learned that 74% of the universe is something very weird. Or more accurately, the universe is accelerating. It's the most dominant force in the universe today, and we really don't understand it. And it might be that its origins can be traced back to this quantum bubbling of empty space. And if that's true, it'll be a remarkable discovery, and it will be, again, vindicate Einstein's picture of what his theory should do. But if it's not right, then it could be the end of Einstein's theory of gravity. And it might be that you're just seeing the beginning of that and finding that the universe is accelerating. So either way, to figure this out, you have to go from using alchemy to understand the universe. You have to do the modern day version of that. You have to build big colliders. And also you want to use astronomy to understand how those particles are behaving and their consequences. You're not going to do that through small telescopes. You're going to do it by putting cutting-edge telescopes, in this case, in space. So in both cases, the trick here is that if you want to understand the universe, it's a wonderful opportunity to take the one-time experiment that is the universe and use it as a unique window into physics at the tiniest scales. It's sort of counterintuitive. The universe is huge, but it started in a very energetic state, so it can teach us about the tiniest things in the universe. Okay? And it works because the expansion of the universe takes microscopic physics and stretches it out across the sky that you see at night. For me, the most important and amazing thing about this is that everything I've told you in this lecture, and I'm a lot older than you, but I'm not, doddering. Everything I've told you in this lecture has been discovered since the time my grandfather was born. Which is not very long ago. Think about your own grandparents, how long ago they were born. It's not that long ago. And things can change that much in that time. So it could be in the next century, we see a great number of developments that solve many of the problems I talked about here. But just think what you will understand in 5, 10, or 100 years. I think it's one of the most exciting things you could think about. But I am a little bit biased. Thank you.